Hello friends, in this video I will try to explain the Helmholtz equation, its logic, and how the Helmholtz equation is applied, at least in one dimension. We saw it in our long video, the third video, but I decided to shoot this separately to focus a bit more on this topic, in case you might lose track of that video. Without further ado, I will talk about the logic of the matter. Why is each mode equation important for us? I will discuss that in this video. The importance of each mode equation comes from here, friends. This gives us the formula del squared u plus k squared. U here, k is the wave number. U here can be any field. It can be E or H. And note that the u's here are not vectorial, so we can take them as E and H here. We will only be concerned with their magnitudes. Now, after presenting this in this way, friends, why is this equation expanded? As you know, the nabla operator here also means derivative. Let's write it down here if you want. Derivative in directions with respect to the ground. It's not related to time, friends. Derivative with respect to the ground, and it expands in the second degree, that is, in the way we call Laplacian. Now let's get to the logic of how this is expanded. The logic of our expansion is as follows. Friends, this applies to the region, for example. I will give it again based on the same two examples as we did in the fourth video. It is based on the reflection from a superconductor, meaning all incoming waves, and the fact that part of the incoming waves come and part of them are reflected. The Helmholtz equation is written region by region. So what do we mean by region by region? Here, friends, for example, what separates the regions in this x, y coordinate system for us? What separates the regions? The conductor separates the regions, that is, it separates into two regions as the first and second region. Therefore, this is the first region, and that side is the second region, friends. Now here, Helmholtz is telling me that I need to apply it for the first and second regions. However, I see that since there will be no field in the second region, I can only use one variable from the Helmholtz equation, either through E or H, whichever I have. For example, in this case, there is E. I will expand U by taking E and use a single Helmholtz. So, what do I obtain from a single Helmholtz, friends? From a single Helmholtz, I can obtain all the fields in this region, the part we call the first region. So, what fields are there? There are incoming fields, and there are reflected fields. It means that the Helmholtz equation provides information about both the incoming field and the reflected field. Friends, here, it is sufficient for me to expand one Helmholtz. So, what is the logic if there is such a transitional situation in the dielectric region? Here, I again have a first and a second region. But this time, unlike the example above, the field in the second area is not zero. The fields in the second region are zero because there is no field transition here. The reason is that we have a perfect superconductor extending from negative infinity to positive infinity below, and since there is a dielectric transition part, what fields are present in these regions? And why do I need to apply two Helmholtz equations, meaning del squared u plus k squared u? I'm explaining why I need to apply two. The reason is this. A field comes here, friends, like this. Let's say this field comes, a part of it reflects like this. And a part of it also passes through. Now here, you can solve the first Helmholtz like this. Let's write it like this. You write the first Helmholtz equation as u1 plus k squared equals 0 in the first region, and for the second region, you write it as k1 squared u1 because the wave number also changes. As a result of this solution, you will have information about both the incoming and reflected fields in this region. Here, you write the second Helmholtz equation as follows. You say that this time the names of the fields here are u2. You will likely use E again if such a question arises, because E is given. If H were given, you would use H. And remember, you expand the Helmholtz equation according to which field is given. I will show you shortly how to expand one of them. If you say del squared u2 plus k squared u2 equals 0. Most likely, when you solve this example, you will only find the information related to the outgoing field, because in this region, a part of it has already been reflected from here. After passing here, there will likely be no further reflection, so most likely, since it is going in the positive y direction, you will find a term with e to the power of minus j2y when you solve it at the end. Now, let's take a look at one solution for this, if you like. On the one above, I had solved it again, but let's see how to expand del squared u like this. When you have e, how do we expand this u? By taking it as e, and let's see where we understand the information of both the incoming and reflected fields. Now, if you like, let's quickly write and expand the Helmholtz equation for this. As a result of the Helmholtz equation, we will obtain the information about all fields in the first region, meaning which fields are present in the first region, both incoming and reflected fields, from the Helmholtz equation, friends. Now look, I am writing the Helmholtz equation. So what will that be for me here, friends? I will take the field information I have. Now, which component will this be, friends? Of course, it will be my E's component. You know about polarization. If you don't, let's learn it like this. The direction vector next to this magnitude we call amplitude tells me which electric field component I have. The direction above the exponential shows me the direction it is moving. Here it says y, which indicates the direction it is progressing. Since it is negative, it is a wave moving in the positive y direction. And it has to be that way in the drawing because we have labeled this as positive y. Therefore I have Ez, and the part we call the function of this Ez is taken from the exponential. It is a function dependent on y. Now let me quickly show you what I mean regarding this down here, friends. We are writing the Helmholtz equation down like this. And let's try to show how it is solved, if you like. Now look, I said that it is enough for me to write just one Helmholtz equation here, specifically E. You know, I need to write one Helmholtz equation E, and I will try to show that it comes from a single Helmholtz equation for both fields. Let's see if we can see it. We write it like this. Look, I am applying the Helmholtz equation. I am applying the equation del squared u plus k squared u equals 0 there. And I know what del squared means, friends. It is the second derivative with respect to direction and orientations, that is, with respect to the ground. And previously, what field do I have in terms of area? I have S, friends. How did I understand this? I repeat, when I look here, I see that it is the S component. The amplitude indicates which electric field component I have, depending on which function it is related to. And it becomes clear from the direction of progression, that is, from the exponent. Don't forget this. This is a function dependent on y. I say this e because if you take its derivative, you will get a result with respect to u. Z does not contribute anything here. While this term gives a result for y, when you differentiate it, if you take its derivative with respect to z, pay attention that it does not enter the operation because it is already directed with respect to z. If you take its derivative wrtz, you will obtain 0. The function depends on y. This is logic of the situation. Now here, I know what function it is dependent on. Then it is a function dependent on z. Let's denote it as small y. Let's denote it briefly as y. And now I know this. Look, this is the derivative with respect to the ground. So when you see this, it can also be written as partial derivative with respect to xe to the x plus partial derivative with respect to y plus e to the y. As you know, you will remember this. As partial derivative with respect to z e to the z. Since this is squared, we have no operations related to directions here. You can think of it directly like this. Since it is squared and my function is dependent on y, I say that only y comes from here. And because it is multiplied twice, e to the y times e to the y is 1, so you can write this directly. Del squared u, meaning my u here is a function dependent on ez and y. That's why I wrote it as del squared y over del y squared. Friends, I'm done with that part. Then k squared u. Which u? It is again dependent on y. I say it equals 0. After this it turns into the classical part of solving a differential equation. So how is it solved here? Let me show you that as well if you want. My goal is to isolate k squared. If I multiply the entire equation by 1 over y, the y's will cancel out and it will become an equation like this. 1 over e comes here. There's also del squared I over del e squared here. I wrote it like this. Plus, due to the multiplication of 1 over y and y, a k squared comes from here. and since it equals 0 on the other side, it becomes 0 like this, friends. Later on, in order to solve such an equation, you logically think about how I can equate it with these constant terms when you look at the equation. Oddly, you equate it with the constant terms like this, friends. If this region equals k squared, let the entire part be minus k squared, so that minus k squared satisfies the equality of 0 in k squared. So what do I know? 1 over y times del squared e over del I squared equals minus k squared. The solution of such an equation is done like this, friends. You say y equals a, which is an unknown scalar of magnitude, times e raised to an unknown alpha. And since the direction vector the variable is related to is y, I can say it is a times e raised to alpha. This sine can also be written as a times sine, like this, friends. But I will use exponential. I will explain the reason for using exponential shortly. You do it like this, friends. Since the solution of y is something like a times e raised to alpha y, look, I have y here. I can write a times e raised to alpha y in its place. I also need the second derivative, therefore I am taking the second derivative of this. So how is the second derivative taken? First I take the first derivative. It is del over del I. What's the derivative of this exponential function with respect to y? A is here. The alpha next to y comes along like this. It is in the form of e times a raised to the power of alpha y. Later on, since I need the second derivative here, I am immediately writing the second derivative like this. Let's write it like this, friends. I say del squared e over la squared equals. Taking its first derivative is enough for me to find this derivative. Therefore, here again, alpha is a constant number, a is a constant number, and you know it just comes down next to y. In this way, it becomes a times alpha squared, because there was one alpha from the previous one. The result comes as a times alpha squared times e to the power of alpha y. So what do I know? The entire equation is equal to minus k squared. My goal is to reach y in some way, friends. Therefore, I set the entire equation equal to minus k squared and say, let's do it like this. I said 1 over should be equal to a times e to the power of alpha. Multiply. There is a second derivative here. Look, what is the second derivative equal to? A times alpha squared times e to the power of alpha y. What is it equal to, friends? Negative k squared. Now, when you look at it while it's a band, friends, if you see that the a's are gone and the e to the power of alpha y's are gone, what is left in the end? It is equal to alpha squared, negative k squared. A series that is normally greater than k0, so something like 3 to 5. Let's say it's 9, negative 9 something. If it's negative 9, my goal is to find alpha anyway, because I am trying to reach y, because y is mine. The main thing I am trying to reach is the most general easy. That is, the easy equation that will provide information about all fields, the easy component. So what is alpha here, friends? You know that if x2 were 9, you would say the roots are plus 3 and minus 3. So what do you say for the roots? If it's negative 9, friends, plus minus 3y. Right, so if I take the square of 3y, it becomes negative 9, and if I take the square of negative 3y, it also becomes negative 9. Therefore, since k itself will be a number greater than 0, I can automatically say that alpha equals plus minus k. After finding this, friends, what I have found is that alpha is equal to a times e to the power of alpha y. Since I found two roots in differential equations, what is equal to y? Actually, what is equal to y is e. So my goal is to reach e. Now can I write it this way? My goal is to reach e, and I know that this e is y. And I found y as a times e to the power of alpha y. One root of alpha is minus jk, and the other root is plus jk. Then, in differential equations, this is written as a times e to the power of minus jk. What is next to alpha? Of course there is y. It cannot be without a variable. I say it depends on y. In this way, a plus is immediately added in differential equations, and I don't know the second root, which is unknown to me. And I don't know y either. But information about fields has started to come to me. I wrote e times one root. This way, I wrote the other root, plus jk, in place of alpha. And since my remaining variable is still y, I wrote it this way, and opened every term, friends. Now in this result I found there is information related to e Actually, what does this E tell me? Now I will tell you, friends. I told you from the very beginning that this E, for which region did I take it, applied Helmholtz for the first region. Why was there no need for me to apply it for the second region? Because there was no field in this region, I had no need to apply Helmholtz here, and if I were to apply it for this region, Helmholtz equation would provide me with information about every field reflected in this region. The logic of the matter was like this. Now I am looking what could be in this region. In the first region, a field could come to the first region. A field could be reflected from the first region. The reflected field reflects with a certain magnitude. The incoming field reflects with a certain magnitude. So, whatever happens on the exponential of this reflected field, I understand that it is plus y. If I see that it is minus jk, I understand that this field has come. So how do I understand how it reflects? If it is plus jk instead of minus jk, I understand that it is reflected. I currently have no information about the magnitudes. So what does it mean that I have no information about those magnitudes? This means that A and B are not known yet. But friends, what direction does this minus jky indicate? Here it is. This is my wave going in the positive y direction. And which field is this, friends? This is the wave going in the negative y direction. So who is going in the positive y direction? Actually, when I look at it, I know it. Look, it means the wave going in this direction with the magnitude E0. So, my variable that I call here is actually E0, as Helmholtz shows me in some way. But I don't know B. I don't know B. In this case, using the boundary conditions, as we discussed in the previous video, my goal is to reach the unknown B. Friends, who will be B now? If you calculate B, with which magnitude will it reflect here? I can actually see that too. Why do I know? Logically, I say that if this is perfect, meaning there will be no energy loss due to being a superconductor, it will reflect with the magnitude E0, but I need to solve whether it rotates too much or not, whether it rotates with minus E0 or plus E0. However, I am sure of this. While it is minus jky, it must also be plus jk because it needs to go in the negative y direction. Like this, which we found. So, as you can see, in this region, only the unknown B remains. In boundary conditions, we find the magnitudes that we couldn't obtain from Helmholtz by applying the method we call boundary conditions. I hope that after watching the previous video and this one, you gradually develop an understanding of the logic of the events. This was one direction related to Helmholtz. It could also be in two directions. Of course, there would be two additional components next to this. We will have examples related to this, but first, it was necessary to understand these parts a bit. I hope you have understood it to some extent. I also predict this. It will be E0, but I'm not sure if the increase is negative. Actually, I'm sure it becomes negative when it rotates. Just like when you send a spring to something, we sent a spring to a fixed end, it would reflect and rotate in the opposite way in physics. This also shows that the phase is rotating. Friends, that's what the event is about actually. Hope to meet in another video. Goodbye.